430 is the last one. 45, 49.
Now you'll see why it's so hard. In a couple of seconds now.
And then those questions, let's say
Back, you'll see it in about 10 seconds.
I'm talking about hands.
41.
This is.
Yeah, right? Yeah.
Still have an after school.
I think it's done Friday, so before the break.
Okay, so we have a surface. Alright, settle down, we're going to begin. Quiet. 4x plus z squared between x equals 0. Alright, so they already gave us the limits, so I don't really care what the surface looks like. I know how to set up the integrals. Just going to have the limits. X goes from 0 to 1, z goes from 0 to 1. So that's easy. And of course, I'm going to use the easy formula for the normal vector, right? Because I'm given an explicit function here.
Yes.
Right? I have y is equal to f of xz. So I'm just going to use for the normal minus fx1 minus fz.
So the only problem is the integral.
So then, this I'm going to be partial with respect to x is 4.
Negative 4?
Yeah, negative f of x, right? So it's minus 4 comma 1 comma partial with respect to z is minus 2z, right? So this implies the magnitude of the normal is 17 plus 4z squared. So the area is going to be equal to the double integral of 17 squared
So
z.
z is equal to parentheses 17 over 2.
Z goes to 0, this goes to 0.
So z is equal to radical 17 over 2 tangent theta.
Wait, yeah, hold on. So I set up to do the x first, right? So if I integrate with respect to x, I just get the thing back, right?
Yeah.
Right, so now you're going to have to try to figure out how to do this. Obviously, the substitution won't work because you don't have a z on the outside, or an odd power of z on the outside. So trick sub would be the way to go. The trick is to look at this as the following.
1 plus 10
Radical 17 squared plus 2z squared. Right, so this sort of reminds you of a squared plus x squared, right? You have a constant squared plus a function squared, and you know that the trig sub for that looks like x equals a tangent theta, right? Here your x is 2z, your a is radical 17, so let 2z equals radical 17 tangent theta. This implies z is equal to radical 17 over 2 tangent theta. And so this implies your area of, doing a trig sub on a definite integral, you always change the limits, right? You don't want to have to back substitute anything. So when z equals 0,
then 0.
theta is equal to 0, right? When z equals 1, theta would be equal to
tangent of 2 over radical 17.
tan inverse of 2 over radical 17. Okay, and this guy will become what?
Radical secant squared. Wait, we need our d theta.
Right, we need our d theta. Forgot to write that down. dz would be equal to radical 17 over 2. Derivative of tangent is?
Secant squared.
Now I can write down the a. So my a is going to be equal to the integral from 0 to tangent inverse of 2 over radical 17 And so this would become radical of what?
Secant squared theta.
10 theta.
17 secant squared theta.
17
Secant squared theta.
secant squared
Times secant squared theta.
times
Yeah,
radical
17
17
secant
over 2
secant squared theta.
secant squared theta. And so this would be 17 over 2 of secant cubed.
Now you have to use integration parts.
Right, so now the annoying thing is integration by parts, and it's going to be one of those where the function repeats and you have to bring it over
Yeah.
equal signs. One of those revolving integration by parts.
Let's do it.
But you do that so often in Calculus 2. Secant cubed was actually on a couple finals in Calculus 2, so it's one of the things that you should have memorized. Theta. That's
Yep.
going to be your integral.
Yep. And we actually need to plug in the octane, don't we?
And so 7 over 4 times secant of 10 inverse 2 over radical 17. 10 of 10 inverse 2
I'm so glad I got it right. The definition right there. Yeah, it's a lot of work.
Alright, that's going to be your answer. And you actually can evaluate secant of tangent inverse.
Yeah.
The idea would be, you set tan inverse of 2 over radical 17 equals theta. This means that tan theta equals 2 over radical 17, which means you can construct a triangle where tangent is opposite over adjacent. Right, by the Pythagoras' theorem, this would be the radical of 17 plus 4, which is radical of 21. And so then you know that secant of 10 inverse of 2 over radical 17 is equal to just the secant of the theta, because my theta is that. And then secant of theta is hypotenuse over adjacent. So you can actually replace this with just plug it in there, and you'd simplify and you'd get the answer.
Do we need to simplify ever? Or can we just keep it as the form of a...
Well, on a test, I would expect it to simplify, but you'd never actually get anything this crazy on a test. It's sort of a weird,
That's what we were looking for.
a ones off.
Yeah.
Yeah.
What's that on the top? Secant theta?
Yes, secant theta. I made an X before, it was a typo.
And there's no upper bound.
Huh?
There's no upper limit.
Yeah, but I couldn't fit it. It should be the same upper limit there. Tan inverse of 2. Yes.
If you memorize a theorem that avoids all this, you can just write
What
it.
theorem is that?
It was on like the reference page.
The integrals mean?
You mean where it tells you that this is that?
Yeah. But no, where it tells you that 17 plus 4b squared equals something else. And you skip all of that.
This particular integral was in an integration table?
Yeah.
In the back of the book, it has an integration table with many different
17 plus 4 sets.
It has a generalized form.
Oh, okay.
100.
Okay, yeah, if they give you like a constant plus something,
Yeah.
sure. Yeah.
No, but the thing is, why can't we use integration tables?
But just make sure you would know how to do it on
Some
paper.
schools don't use them. I mean, some schools use them though.
Yes.
When you have A equals the integral, where did you get the square root of 17 secant squared theta?
From over here, my trick sub.
No, because the limits were
Right.
0, 1.
If this guy, if my 2z was radical 17 tangent theta, right? So it means that this would become radical 17 squared plus radical 17 tangent theta squared, right? Which I can factor out 17 and I would get 1 plus tangent squared. which gives me 17 secant squared. I plugged that my thing in here, and then I used trig identities to simplify that.
Okay.
Any other questions?
It was an interesting problem figuring it out. Though.
Yeah, the integral was the toughest part. Well, with all of these, the integral is the toughest part because it's more or less you're always doing this formula: a equals the magnitude of the normal, and you just have to decide: are you going to use the easy formula for the normal or the cross product formula? And I said, well, you don't use the cross product if you're given a parameterization.
If all right, so not this particular example, but if something like this was on a test, and you knew the formula and you just stated the formula, would you have to write that the normal vector is equal to that before you go into everything?
Oh, you mean like write this down?
Yeah.
Technically, no.
Okay.
But it is to your benefit that you do write it down because you see if you like write this down here and then you make a mistake here, I will know that, well, at least they know the concept. They probably just, they made a mistake here. But if you just write down a random vector and it's wrong, then I'm going to like, where did this come from?
Like, for example, for mine, I didn't put any vector at all. I just wrote the equation 1 plus y sub x squared equals y sub z squared, and then that's the surface area equation. So, I mean, there's no need to write vector, right?
Yeah, you're doing the calc 3 way, where you know that the area is the double integral of
so it's not necessary
the partial square plus this.
It's not necessary to write any vector in doing this, right?
No.
No. How did you use the triangle anyway?
Come here.
How did you use the triangle? I wasn't really...
I want to find secant of this guy.
Yeah.
Well, the tan inverse of something is just an angle.
Yeah.
So I set it equal to an angle. Then I solve for tan theta of that.
Okay. Oh, okay.
I know tangent is opposite over adjacent,
Yep.
so I get to write this triangle with the opposite over
And then
adjacent.
you just did...
Pythagoras' theorem gets me this one.
Yep.
So then I have a fully populated triangle. I can figure out what is the
Okay,
secant, the
easy enough.
sine, the cosine, whatever.
That's it.
Should that be second data plus tangent data instead of 9?
Is it a plus or a minus?
The plus.
Is it plus?
The plus.
Okay. I mean, you could check. You differentiate and you can try. I thought it was a minus.
No.
You sure it's a plus?
Yeah, it's a plus. Okay. From the equation.
Okay. Yeah. Doesn't matter. I'm taking the magnitude. It really doesn't matter which direction it's facing. Yeah. In what we're going to do in this section is going to matter, but here it really doesn't matter.
On a test, when if you ask a question like that, do you have to explicitly write out what the normal vector is, or can you just do it?
No, you can jump to the, in this form you could jump to the calc 3 formula, the radical of the partial squared plus partial squared plus 1.
So why do you guys problem like this anyway?
It's good practice. Right? The setup is the important part. Once you understand the setup, the integral is just a formality. So, and you won't really get anything like this.
You might go
Huh? Wait, what were you saying?
I was gonna say, are you still gonna do more homework questions?
Sure.
Yeah, sure. I'll do a couple more. Maybe. So you wanted 38. So find the area of the surface. If I just set up the integral, you'll be able to take it from there, right?
Yeah. I mean, this was the only hard one.
Yeah, this is the hard time the whole homework.
33. So you want 3x plus 2y plus z equals 6. First option. So you can draw a picture if you want to help you out. What's the intersection on the y? X.
Equal to 0.
2. What about the y?
3.
The z.
6.
Yeah.
So you have this plane, right? And you want to find the area of that plane, right? And since z is already nice, I can just solve for z. Take that to be my f of xy, which is equal to 6 minus 3x minus 2y, right? And so I'll be taking my region of integration in the xy plane. And so then the area is just going to be equal to the double integral over d of the radical of fx squared plus fy squared. All right, so if you write that down instead of explicitly telling me what the normal vector is, that's also fine. And then this would be the radical of, this is, well, it's going to be 3 squared plus 2 squared plus 1. Which is the double integral of square root 14.
What's the limit?
So if we want to get to the limits, we could. We don't have to. Right? I could say that this is just the radical of 14 times the double integral over d of dA. I know that this is just the area of d. Right?
It's kind of odd to get a...
Where my d is a triangle, right? With base length is 2, height is 3, so I can just use half base times height. 1/2 base times height. And then you get 3 radical 14. Why didn't you write radical 17? If you wanted to do actually set up the limits, you'd have to realize that the following is happening. For example, if it wasn't a constant, then you'd have to set up the limits to do it properly. But since it's a constant, you can take the easy way out and just find the area of the region. So if you wanted to set up limits, you can redraw what your d looks like. It's 2 on the x, 3 on the y, right? This is your d. So I can let, for example, x goes between 0 and 2, right? And let my y goes from 0, which is this function, up to that function, right? And you want to figure out what that function is. Well, that's this function in the xz plane, in the xy plane, which means you just plug in z equals 0. So this guy is when z equals 0, because you're in the xy plane, so that's just a curve of 3x plus 2y equals 6. Or you can write it as y is equal to 3 minus 0 to 2x. And so your area would be integral from 0 to 2, 0 to 3 minus 3 over 2x, radical 14, dy dx, which you would get to the...
We're free to use any formula we want as long as we get the right answer.
Okay.
Alright.
Any other questions?
Can we go with 43?
Last one. So in 43, we're given a parameterization. The x is uv, the y is u plus v, and the z is u minus v. And we're given the limits. These are bounded by the cylinder u squared plus v squared equals 1, or the circle. Alright, so here I'm given a parameterization, so I'm just going to use the r sub u cross r sub v to get the normal and take the magnitude. Alright, so here I have r sub u, v, 1, 1, r sub v,
U1 and 1.
u, 1, minus 1. This implies my n is just going to be the cross product of these guys. So that's minus 1, minus 1, minus v, minus u, but you take the negative, v minus u. This implies the magnitude of my norm is going to be the radical of 4 plus u plus v squared minus u squared, which we can simplify. 4 plus u squared plus 2uv plus v squared plus v squared minus 2uv plus u squared. And these guys cancel. So I just get the radical of 4 plus 2 times u squared plus v squared.
Which is R.
Which is going to be r, yeah, u squared plus v squared is going to be my r squared.
And that's just default coordinates.
So a is just going to be integral over d of the radical of 4 plus 2 u squared plus v squared dA. Bipolar. R equals r cosine. I'd let this be the u, this be my v, and then I would get my area is just integral from 0 to pi 0 to 1 radical of 4 plus r 2 r squared r dr dθ, and u substitution plus this.
Yep.
Okay, so last time I really introduced like 2 new formulas, but the concepts surrounding them are going to be pretty important, and we're going to start to see just how important in this section. All right, so recall what we did last time was that we found that if a surface is parametrized by a vector function, then the normal vector to the surface will be given by RU cross RU, right? Where RU is just a partial of the components with respect to U, and get a vector partial with respect to V, get a vector, you get that. If the surface has an explicit equation, example, you can actually write it out as z equals f of xy. Then you take the normal vector to be something like minus fx minus fy positive 1, right? This happens to give you a certain normal vectors the upwards one,
Yeah.
right? As far as area is concerned, we don't care because we're squaring all the components anyway. It doesn't matter which ones are positive or negative. But so far, that's what we had. And I said that you use this if given a parameterization or it is to your benefit to parameterize.
Otherwise, it's easier.
Right? And I mentioned some situations where it might be to your benefit to parameterize. For example, one of my examples was, a cylinder running along here, right? Where the normal vector would be pointing straight out to the side. It's not up or down. The z-coordinate is 0, and so a formula like this would not work because the z-coordinate is 1, right? So in a case like that, you couldn't do it, right? But if I had something like only a half cylinder, that's, for example, only given by the part where y is not negative, then what I could do is I could solve for y. I could say y would be equal to the radical of r squared minus x squared, and take that to be my function and do it, right? With the other side, I would get the negative radical. Having two functions, I'd have to do two integrations, right? It's not to my benefit to do that. I would just parameterize.
Technically, is it still possible to do the 2 iterations?
Yeah, you would be able to do it.
Oh, so it's one that allows us for that. So when,
If you want to do it that way, fine, do it that way.
Alright,
Just
nice.
make sure you get to the answer, right? But in situations like those, as opposed to doing 2 integrals with 2 different normal vectors and 2 different surfaces, it's better to just bite the bullet, parameterize, and just do one integral.
Yeah.
Right? And here it's if function is given explicitly or you know an explicit equation for it. For example, in one of your homeworks, one of the first problems, they gave you a vector function that they wanted you to describe. It was something like r of st equals t s, I think it was t squared minus s squared, something like that. Yeah. Well, you just know if you let x equals t, y equals s, the z would be y squared minus x squared. Right? So this is really just describing the surface z is equal to y squared minus x squared. And so you can go from this parameterization to that and then use the easy formula. Minus fx minus fy positive 1. So if you recognize it and you can get an explicit equation, I would suggest you get the explicit equation and do it this way. A lot of times the cross product is going to be a lot of work, especially if you don't have all constants, right? If you have functions in these vectors and your cross product with functions all over the place, it gets confusing, right? It's much easier to do this. So try to do it this way as much as possible. That way it's like you have to. And of course, we covered things like the area is just the double integral of the magnitude of the normal dA. So those are the formulas. And in this case, we don't care which normal vector you take, if it's the positive or negative, because you're taking the magnitude. But it is going to matter which you're going to take, and that is coming up soon. When we talk about oriented surfaces, we orient them by the normal vector. So the direction of the normal vector will matter. But so far, it doesn't matter.
Why do you need oriented surface?
We're going to talk about it. It's just for a general application. So for example, in physics, if you're modeling, like electric current over some surface, right? Whether electric current is like pouring out of it or going into it, you'd want to know things like that, right? The direction of the flow.
Like static?
Yeah, you'd want to know the direction of flow. That's what we're trying to measure here. So direction is going to be important when you're talking about surfaces sometimes. But so far it didn't matter, but know these concepts well. You're going to need to know how to find a normal vector right away, and you're going to need to know the easiest way to get to it. Yes.
So one would use these kind of things for like Gauss's theory type stuff?
Yeah. Yeah, there are a bunch of them. Especially in 208, things like electromagnetics and stuff like that.
So this is section 13.7?
No, this is a recap of 13.6.
No, but what will we do right now?
13.7, I'm going to show you where this comes into play. Yes, we're going to do a different kind of integral. We've done line integrals. Now in 13.7, we're going to talk about surface integrals.
What do you refer to with up? Up?
Oh, because the z coordinate is positive. Your z component is positive, so your vector is sort of pointing in the positive z direction. That's why I call it up.
So we have two more sections, and then we're in our next book.
3 more sections: 13.7, 13.8, 13.9.
Okay. Yeah. And then
yeah.
So after that, we'll be done with the calculus.
Yeah, and we're going to move on to linear algebra. So let's talk about 13.7, surface integrals. So remember, the line integral was just a generalization of the single integral that we learned in calculus, right? Back in Calc 1, they told us, oh, you can integrate over some interval on the x-axis or on the y-axis. But then they never told you how to integrate on some arbitrary curve. Similarly, in Calc 3, when they're introducing double integrals, they said, oh, you integrate over a region in the xy plane or in the xz plane or the yz plane. But they never told you, what if you want to integrate over some arbitrary region in space? Right? Not in one of the planes, but just any surface in space. What would that look like? Well, it's going to look like a surface. want to say arbitrary, but arbitrary smooth 2D surface in 3 space. Not just a region in the xy plane, xz plane, etc. Right? So in Calc 3 they told you, okay, you're going to integrate this thing, but you're integrating over this projected region. Right? Here we're not going to do a projected region. We're going to actually integrate on some surface suspended in space. That's what surface integrals are about. And so we are going to talk about the definition right now. So assume we have a parameterization for our surface. Defined on some domain D in the UV plane. Let f of x, y, z be a scalar function continuous partial derivatives over D. Mathematicians like to tell you exactly when you can use something. So that's all they're doing here. They're setting up the context. Of course, in 392, all this will be given. You never really have to check it. We're always going to give you nice surfaces over nice domains. But if you have all this fulfilled, then what we call the surface integral of f over the surface S is given by finally. The double integral over S is the notation of this function d big S is equal to the double integral over d of plugging your parameterization into the f and multiplying by RU plus RU.
So small s is arc length, big S is surface.
Yes.
All right.
So that's the definition. Right? So compare to the regular line integral when we had the integral along C of f of x, y, ds, little s, right? That was just equal to the integral of f of r t times the magnitude of r prime of t dt, right? That was our guide. Here we have a very similar guide, except we have a double integral, and instead of the magnitude of the derivative of a vector curve, we have the magnitude of the normal. And our parameterization here now is in 2 variables, not just 1, right? So really upping everything by 1 dimension, right? And that gives you the definition of the surface. So we're entering the point where we're going to have a lot of similar notations for a lot of very different things, right? These two are not the only ds integrals we're going to have. Eventually we're going to have a d vector s integral. But so far we have the d little s integral and the d big S integral, and they're actually quite different. This one is a single integral. Right? We know that the definition of f ds is just the integral of f of rt times the magnitude of r prime of t dt. This guy is a double integral, and we know that the definition of f d big S is equal to the double integral of f of r u v times the magnitude of the normal vector. So they're actually very different. This guy here, if you want a concrete interpretation, there's a random curve in the plane, and there's a function f of xy, right? This gives you the height of the fence. Then this guy is equal to the area of one side of the fence. This guy, if you're in 3 space, this is going to give you some function here, x, y, z, and here's your surface S, and it actually gives you the volume
Also arbitrary surface.
over S under the F. Right? So that's the concrete interpretation. Of course, we never really use this interpretation for the single integral, so we're never really going to use this for the double integral, but that's really what the number gives you. Of course, we're going to apply it to other contexts. Yes?
So if we find volume of some oddly obscure type of shape, we would then use the capital S, right?
Yeah, you could use the surface integral, the ds integral to do that, yes.
So do we do that in real life?
No. Usually when you want to find volume of something, you do it the calc 3 way.
Or you can measure it. I don't know. But yeah.
You wouldn't go through the trouble of parameterizing something and finding normal vectors and all that. Just do top surface minus bottom surface, double integral. Yeah? Once you can actually map the surfaces. Okay. So far that's what we have. Right? Call if given the surface explicitly, say z equals f of xy, right? So instead of saying something equals f of xy z, suppose we can actually take this guy and solve for the z on some level curve. Then we can say your normal vector can be given by minus f x, minus f y, positive 1, and so double integral over s of f of x, y, z ds. You can actually also write that as f of x, y. I already used f here. Let's call this a different way. Partial of z with respect to x and partial of z with respect to y. And I can say f of, just plug in the z here, and then over here, just do z sub x squared plus z sub y squared plus 1 d8. Right? It's actually an equivalent formula. Right? It's just that you're using the trivial parameterization that we spoke about. And you can actually write the integral in that way.
We have to do it the hexagon way,
Right.
vertical way.
So again, I can call this guy formula 2, call this guy formula 1, and the same recommendation applies. If you're given a parameterization, use 1. If you're not, if you're given explicitly, use 2. because cross products are annoying in general. Right? Try to avoid them if you can. Okay, and so that's the theory. Let's do a few examples. Should mention this. So far, we still haven't gotten to the place where the direction of the normal matters. That is an example.
Is there like a f.dr version of your space stuff?
Yes, we're going to do an f.ds integral.
And what is that calculated?
Volume.
Flux, calculus flux.
Flux?
Yeah.
You mean electrical activity?
Yeah.
It can be interpreted that way if your vector field is interpreted as an electric field, yes. Right. We're going to do the equivalent of the f.dr integral. It's going to be the f.ds integral. That's going to be with a vector on top of here. But that comes later. That's later in the section. Right? Right here, we're still doing a scalar integral. It's not an integral over a vector field. It's still over a scalar field f.
But generally, scalar field same thing like
Come again?
But the method is the same for both scalar and vector, or?
No, one you're going to have to take dot products. This one you're just multiplying two times.
Alright.
We'll deal with it later.
So for this, you would want to put it in terms of z first?
We could solve for z. I mean, we'll get fractions, but it's probably okay. You could solve for z or y. If you solve for y, you don't have fractions, but your integral is going to look a lot uglier because you're going to have to replace this y. If you solve for z, you'll get fractions, but your integral will be smaller. It's up to you guys. You don't fear fractions, right? So set z to be equal to what? 3 minus x minus y over 2. Right? So z sub x would be minus 1, z sub y would be minus a half. So the magnitude of the normal would be minus 1 squared plus minus a half squared plus. This is radical 2 plus a quarter. 2 is 8 over 4, so this would be 9 over 4. Alright, so the magnitude of your normal is 3 over 2. What does our region look like, the region of integration? set up a picture.
Yeah.
Since I solve for the z, I know the region of integration is going to be in the xy plane, and it's a plane. If I plug in y and z equals 0, I get x equals 3. X and z equals 0, y equals 6. And x and y equals 0, your z would also be 3.
Now
I know this is my region. Set z equals 0.
We don't actually need to integrate, do we? Do we need to integrate, or can we just do what we did before?
1/2 base times x.
No, we have a function
Oh,
for variables.
yeah.
It's not a constant,
Yeah.
so the area of the region is not going to be.
Alpha, yeah.
Right, we're still going to have to integrate this function x plus 2y. So there are variables in there. We need the region. Right? So now the region. So the region is in the xy plane. Your x goes between 3. Your y goes between 6. And if you just set z equals 0 into that guy and solve for y, for example, you would get that this line is y is equal to 6 minus 2x. Right? And so you can set up your region. X goes between 0 and 3. Your y will go between 0 and 6 minus 2x. And so now you can actually set up this guy. Is it 6 minus 2x? X plus 2y. Right, because I'm parameterizing x is itself, y is itself, z is blah, but we don't have z, times the magnitude of normal, which is just 3 over 2. dy dx. And so, 3 over 2 on the outside. And we integrate with respect to y. This would give us xy plus y squared. 0 to 6 minus 2x. So plug in 6 minus 2x for y. I would get 6x minus 2x squared plus 6 minus 2x squared minus 0. So we just get that integral. All right, from here on, it's just like validating calc 3.
Actually, no, it's calc 2, actually. This one.
Well, at this point, it's calc 2. Yeah, this was calc 3. Okay, so expand or whatever.
Yeah, expand.
But if you want to integrate this, what I can do is just, this would be what, 3x squared? Minus 2/3 x cubed plus 6 minus 2x cubed over minus 6. And so we would have 3 over 2 times, plug in 3 here, get 3 cubed, that's 27. 3 here, get 27 divided by 3, that's 9, minus times 2, that's 18. Plus, plug in 3 here, you get 0. Minus, plug in 0, 0, you get 0. Over here, you would get 6 cubed over 6.
6. So 6 squared.
Right, so 6 squared. So this is 3 over 2 times 27 minus 18 plus 36. What's that?
Nine times 45.
45. And 3 times 45?
Yeah, 45.
135.
Yeah,
135 over 2.
Okay.
Professor, in real life, what would the x plus 2y represent in the case where you have to use this kind of mathematics?
It would represent something like the volume interpretation. This one, it's sort of weird, like when you were doing the single integral of f ds. I mean,
Doesn't really represent.
you didn't really do anything. The really interesting one was the dot, the one with the dot product, right? That one we're going to talk about the applications of. But this one here is just knowing how to do it. The good things with doing these, especially, is that the ones with the vectors, you usually can decompose them into a sum of scalars. So if you have to know how to do these to do the other ones. Yes?
So what's the difference between this and a regular double integral? I really don't see any.
Your ds is different.
But the ds just turned into a regular region in the x and y plane.
Yes, here, because I use a trivial parameterization. Right? There are cases where it's going to be very different. Right? Like if you're given a parameterization, your x is going to be a function, your y is going to be a function, your ds is going to be a whole other function. So you're really plugging in a lot more stuff into this guy. This was just a very nice example. Right? I just started off with a nice example. Right? First ones, you try to make them nice.
And so the surface can also, like, the function that you integrate, since it's actually like kind of like a pore space, I guess you can think about it. The volume
Yeah.
kind of like a pore space.
It's like a hypervolume, and we're integrating over a level curve in,
Well, I mean,
in force
it's not a hypervolume, it's just the volume exists within the pore space, kind of.
Question.
in 3 space. But the important thing to realize here is that we're not actually integrating over this region. We're actually integrating on the plane itself. And that's why this integral is different from a regular double integral.
You said we'll need to decompose eventually, right? We'll need to decompose vector functions using scalars, right?
You can.
Like
I showed you, for example, before, that f dot dr.
Can be decomposed.
You can sort of think of that as, you know, p dx plus q dy.
Yeah. Okay.
Right? So if you know how to deal with scalar integrals,
Yeah.
in theory you know how to deal with vector integrals.
So
there's a lot
this
of...
translates into.
Yeah, it will translate. We're going to deal specifically with the higher dimensional version of f dot dr.
So we just add like a w dx, d something, like wdz.
The interpretation of the double one with the dot product is flux. It's not going to be work anymore. It's going to sort of the flow, the direction of flow between the surface. Actually, don't think I have time for the second one. Okay, so we'll sort of end there. So we'll finish this section next class. So no homework to do because we didn't finish. And we'll start the next section, which is good because you'll have like ammunition for in case I put a bonus problem on the second test. But yeah, so the second test is after spring break as you come back. So. First, I'm going to use all the axes I possibly can.